Hi everybody. So today I've got two goals. One is to give you examples of using Fabric's programmable networking hardware, and the other is to provide you with a starter kit for your own work. So I'd like it if you could go away from this. So my measure for success for this talk is if you went away from this with two things that are clear: what can this resource do for your own work, and an actionable path towards getting there, right? So it's integrating towards your work. Now, in the context of this work is driven by my interest in programmable networking. So programmable networking is a take on networking where the network plays a more active role in moving data across the network and making it also amenable to making the network more amenable to doing some processing along the way opportunistically in order to enable better performance as well as richer features. And I see this as being a fundamentally important part in implementing modern distributed systems with their ever-increasing demands. So in the course of this talk, I'm going to be drawing from that experience and giving you examples, concrete examples in two particular application domains that I'm interested in. One of which is cybersecurity, and the other is research network infrastructure. I do various projects related to research network infrastructure, but in today's talk, I'll be focusing specifically on Fabric. So to begin with, let's have a demonstration. And what you're seeing here is a demonstration that is of a Fabric, something running in a Fabric notebook, right? So in case you haven't used Fabric, one of the really cool interfaces that it provides you to use the resource is Jupyter Notebooks. And it also provides other kind of other ways of interfacing this. And what I've done for here is I've kind of played a bit with widgets and showed a way of implementing a simple calculation on Fabric. So I've titled this integrated computation, and the focus here initially is going to be on the computation part. And the computation consists of an addition. Okay, that's not very impressive, but it's a start, right? So it's something basic that we can all appreciate. So what I'm going to do next is I'm going to expand computation, and then I'm going to get to the integration part. So now extending the computation part, well, we can do addition. We have a simple calculator going, right? So I click on subtraction in this case. I'm going to click calculate, and the answer shows up here. And it shows up as 6, which is correct. And you might have noticed there was a little delay there. I'll explain where the delay is coming from and how all this stacks up. So there is other, there's other kind of, there's something that's happening behind the scenes here, because the calculation is not taking place inside the notebook. In fact, it's not taking place inside a host. It's in kind of a host proper inside the microprocessor. It's actually taking place in the network. So now expanding out the picture further, I'm going to rerun addition. And what you'll see is I'm going to reveal a bit about what's happening in the background. So what you can see there happening in the background is that actually we crafted a packet that carried in it a request to perform the calculation. And so just to break this up a bit, what we can see is that the packet is structured into, we have Ethernet, and then we have our operands there that are carried in a custom header, and we have an operator there, it's coded as 43. And 43 is the ASCII character for the symbol that we use for addition. So in there, we've internalized, our request as being, think of it as maybe something like an RPC, but it's not an RPC that's going to be interpreted by an end host. It's going to show up in the network. And there's other things now that we can do, right? Thinking RPC, I've queried the actual substrate that produced that calculation in order to provide version information. And in this case, I'm acquiring statistics to do with frame counts that it processed. Okay, so this is the target that actually carried out the computation for us, right? So this is an Alveo U280. There are many of those implemented in across Fabric. And it's a pretty cool piece of hardware to be able to use. You can see it has a kind of a PCI interface here where it slots into the machine. There are two QSFP ports here, so it has two fully duplex 100 gigabit links it can take on here. And if you were to crack open the if you were to crack open the shell, which for warranty reasons I do not recommend, you were to see it has gigabytes of memory and a whopping big FPGA on which the calculation was actually took place. So the integration part I was alluding to is kind of one of the cool things I appreciate is working with heterogeneous hardware, but also having an interface that allows you to gel it all together, not only for the convenience of doing research or for doing demos, but also for teaching, right? And as we did earlier, kind of unpeeling one layer at a time without jumping into the guts of complexity straight at one go. So in case you're wondering about the background, it's because the hardware that was actually being used here is one in Hawaii. And one of the really cool things that I appreciate in using this infrastructure is the sheer geographic span, right? So this is not something that you can have in a typical university test bed, right? You can't have a continental scale test bed at your disposal, typically, right? But if you were running high throughput experiments, and using specialized infrastructure like this, specifically the FPGAs, across a geographic span with all the complexity that entails, it really ups the game in terms of what you can achieve. So in summary, kind of the takeaway from this is, there are various, several of these devices that you can use on Fabric. Large geographic span, it's a shared resource for the use of the entire community. My own focus, and indeed the focus of my talk, is going to be on networking, because that's the kind of person I am. But indeed, there are various other non-networking use cases that have been proposed for this and indeed used for this, right? So anything related to even including machine learning, of course, anything that is going to be resource hungry, that can benefit from using heterogeneous resources. And finally, there's obviously the high performance angle to this in terms of both throughput and latency, and in the convenience in which this is presented to you, right? So authentication and authorization and through the notebook interface that I described, and also SSH. So in order to get to the two goals I highlighted at the start, I'm going to kind of get to the next kind of layer now and continue unpeeling what we just looked at to make sure that it's all fully grokked. So what we saw essentially here was I ran a notebook, a Jupyter notebook, right? This was running on a commercial cloud. And it's a story like that saying, right? You might have come across it saying, don't believe anything you hear and only believe half of what you see, right? You saw me running the calculation inside the notebook, but actually the calculation was being carried out in a very different piece of hardware, several thousand miles away. So what happened behind the scenes, and this is where we're going to kind of start the journey to get closer to where the action took place, is that the Jupyter notebook made a request to a node that was deployed on Fabric. And this node then essentially interpreted this request and generated a packet, right? So this was the format of the packet that we saw earlier. And this packet included basically that RPC call that I described earlier. And then what happened was that there is, at the other end of this link, and obviously this is a kind of a virtualized link, right? So the Fabric infrastructure takes place of kind of stitching everything up to give you a view, an abstracted view of a network that you control, right? A virtual network that you control, albeit very well underpinned into the resources that you rely on. One resource being that Alveo card. And the request never enters the peer host. It crosses the Alveo card, and it is serviced in the data plane itself, right, on the card itself. So what happens is that the calculation is done on the card, and it is sent back over the link, back to the host from which the request originated from. And the reply reuses kind of the frame, right? So what happens we basically switch the source and destination MAC addresses, and we compute the calculation that was requested, and we populate a field, right? So this is showing you the diff, as it were, of the two slides, of the two packets, or frames, rather. And then in our case, what happened was, and this is kind of that small delay that you perceived, right? Because there were several linkages, right? Several moving parts here, was that the tester node received this frame and interpreted it, extracted the answer, and then sent it all the way back up, right? And now we can think about generalizing, right? So far you can get with addition and calculations, right? Typically, our research, the kind of processing we want to do is of a very different nature. So here we can think about, okay, we can replace the function, the calculation we performed with a different function, right? So we have a function f over there that is computing over x, that is particular frames in a specific frame format, in a custom frame format that you might want to receive. And it then computes an answer that is sent back. But it doesn't stop there. In fact, you can also do some limited switching behavior. For one thing, as you saw, the Alveo has two ports. And for another, 2 ports facing the network. And for another, you have an interface facing the host. So the logic that you implement on these NICs, not only can it be high performance, but it can also take into account some topological features of where you want to embed it in. Okay, so kind of doing a recap of what we just looked at before moving to the next phase. So we're looking at programmable networking here, right? So the general kind of theme I talked about at the start of my talk. And we are carrying out some limited computation in the data plane, right? And here, in case you're unfamiliar with the lingo, we're distinguishing data plane, which is kind of where traditionally mostly the forwarding takes place, right? Based on lookups and maybe some side affecting computations like incrementing counters, and distinguishing that from the control plane, where typically a lot of the smarts takes place, right? If you're running distributed protocols to compute routes, that takes place over a different time scale, requires a very different class of computation grade, and also distinguish it from the edge where the beefy servers are, right? So if you have a big batch job, typically you're going to require a lot of DRAM, right? And that comes with its latency cost, and that can be inconvenient to put in the critical path of something that is latency sensitive. So that kind of takes me back to that limited kind of bracketing that I talked about in the data plane, right? It's both a pro and a con, right? It's a pro because you have guaranteed performance, right, in terms of low jitter and predictable throughput and predictable latency. It's a con because of less expressiveness, but I tend to see that as a blessing in disguise. That it gives you less rope, so to speak, that less expressiveness. So one cool thing on Fabric is that actually there are various ways of manifesting programmable networking, right? So I want to acknowledge I work at the University of South Carolina that involved using a prototype software switch called BMV2 and more recently DPTK-based approaches so that you can do programmable networking on microprocessors. Work at Northeastern and University and University of Massachusetts that target FPGAs. And what this talk is about is the use of the ESNet SmartNIC framework to program these Alveos on Fabric. So this the SmartNIC framework, the ESNet SmartNIC framework, we've been using for quite a while in my group. And one thing I really like about it is that it is not a toy. It's actually used in deployment. And oftentimes when something is used in deployment, it comes with kind of a certain idiosyncrasy and a certain focus that is difficult to engage with as it's an academic, but also also difficult to try to bring students in to use. But something I've noticed here, and I think something that's helped us a lot, is that because of how this was designed, how this is presented, it's actually possible even for people without deep technical understanding, right? In order to it's possible for them to make use of this, right? So I've onboarded several undergraduates, for example, who have productively been able to use this platform. And I think that speaks highly of both, right? Both the platform and its usability, and also the undergraduates and their determination. But it's great to be able to see the kind of a viable path to use a cutting-edge infrastructure, even for people who do not have years of experience with different types of infrastructure. The origins of this platform is to meet the very demanding, the exacting performance requirements at the DOE. And one particular entry point this is part of the secret sauce that makes it amenable to people without deep technical experience in order to utilize, is that it supports the P4 language. So typically for this type of architecture, the mainline way of going about this is to have hardware engineering skills, and you define a circuit either at some level of abstraction, and then you would configure the FPGA based on that. Now, one advantage of using a domain-specific language and the big sell is that you can have non-specialists about the target to productively use the target, right? So DSLs came up earlier in Casey's talk in relation to making queries, right? So we find that thinking permeating computer science, right? There are various types of they used to be called little languages, right, or domain-specific languages that help us carry out specialized tasks. And P4 is a very good. Empirically, it's shown itself to be a kind of a very good entry point, because you'd focus on the logic that you typically describe as a network engineer, in terms of essentially boiling the computation down to doing a chaining of lookups, and the tool chain will translate that into the intricacies of specifics that can be embedded inside the contextualizing architecture. Other pluses is that this framework is extensible. So if you are a hardware engineer, or if you want to customize it in very specific ways that exceed what P4 allows you to do, you can do this. There are multiple ways. You can create externs for P4, or you can create logic blocks and integrate it with the top-level design. And for practicality, and we like to solve things by divide and conquer, and as I'll show you in a bit, it has a streamlined modular workflow based on containers, and this has helped, and this also shows up in how we devise the development phase, and contrast that with the actual deployment phase. So okay, so far I've shown you a calculator, but you can only go so far with that. So now I'm going to kind of focus on the return back to my goals, right? I want to show you what can you use these for based on concrete examples that we built at the lab, and also how can you use them, right? So going back to that starter kit that I promised you at the start. So I'm going to draw examples from my own group's work. So and kind of the bulk of these examples are going to come from research. There are, however, examples of using this for teaching. I find it fascinating to be able to put students into contact with a large, heterogeneous, atypical infrastructure, with all the challenges that brings, right? But that's a good thing, because it trains people to work in terms of not expecting things to just work out of the box and have to do a little bit of problem solving. So there's a couple of courses that I have involved Fabric in, and also the Alveos in, including a course that's currently running on computer networking. But the bulk of my description is going to be about research-derived use cases. So the first one I'm going to talk about is to do with profiling. So this rather connects to what Arpit mentioned and also what Casey mentioned. There are different types of networks, and each network has a recognition. It has a characteristic in terms of what workloads and what cadences it follows, and we tend to kind of categorize this and capacity plan for them accordingly, right? So we think about data center networks in one way, ISP networks in another way, home networks in another way, campus networks in another way, and the open internet in another way. What about testbed networks, however? Right. So in this project, the goal is to understand what does the data plane of a testbed network actually see? Other types of networks have received a lot of interest in the past, right? As Casey said, because there's a very compelling commercial use case, right, for that. But understanding what network testbeds see would also help us in thinking about capacity planning or management of such testbeds, particularly since our hypothesis is that network testbeds can be very chaotic and very messy, because it can depend on a whole lot of other things, right? So characteristically, for example, ISP networks follow a certain pattern that people would leave to go to work, and then they'd show up again after work, and you'd see internet activity kind of correspond to that presence. And then inversely, people come to work, right? And kind of a camp or a corporate network would follow a certain temporal pattern. With network testbeds, I think it's a lot more messy than that, right? And sure, you're going to probably see some clustering of activity, some surge in use in the run up to deadlines. But there's, because of the multi-use reasons of these testbeds, there's going to be deadlines pretty much all of the time. So that's what we want to do in this project. And the way we went about it is, as you know, on Fabric, you set up experiments. And we set this up as itself being a Fabric experiment, but in such a way that it does not interfere with itself. We set this up in this way because it was the most kind of win-win way of setting this up, right? We didn't want to impose on the Fabric people to do a custom solution for us in order to monitor their system. And also for us, it was, anybody can create an experiment. So that was the kind of the most natural starting point. And for this, we leveraged a primitive that is available on Fabric in order to mirror ports. And essentially, what we built is a systematic kind of hoovering of traffic across Fabric internationally over a period of time, and we gathered a lot of data. In fact, one of the as was alluded earlier, one of the challenges is digesting and analyzing that data. And what I'm showing you here is some kind of early results related to that. What you can see on the right, those are a distribution of frame sizes. So I think Casey mentioned this in relation to another project, albeit over the open internet. We're interested in frame sizes because they're usually indicative of what kind of flows you're looking at over those networks. So the different subgraphs are actually different uplink ports at different sites, right? So we've anonymized it. We're not saying which site is which. So, for example, if you look at the bottom row, you have S8.1, S8.2, S8.3. So that's one particular site, and we're looking at 3 of its uplink ports. And one of the things that stood up is kind of a differentiation between, some sites tend very much towards smaller packet-based flows. So if you look at S7.0, for example, right? So you're looking at stuff that's mostly up to 127 bytes, but other sites have huge flows. And obviously this changes over time. But by looking at the picture over time, you're getting an idea of resource usage. And it's not telling you a full story, but it's part of a picture that we're building. Another part of the picture is in this graph in the lower left, for example, where we're looking at header diversity. So how many different types of headers do we encounter, right? And in some cases, you just encounter 4 headers, right? So that's going to be Ethernet, and then it's going to be IPv4, and then probably it's going to be UDP and maybe something else, right? Or maybe you might have MPLS kind of sandwiched between the two. And you can see that the kind of the mean, the mode is going to be in the region of 20 or so, but some sites they exhibit tremendous amounts of header diversity, right? So whatever applications or whatever experiments are being carried out there, they're really exercising a lot of variety. And this analysis, to do this, we ran a big batch job and essentially used T-Shark protocol dissectors, right? So we didn't want to reinvent that wheel, right? There are excellent protocol dissectors out there. We gather these captures and push it through that. So what is the role of the Alveo? So I told you what the role of Fabric is here, right? So Fabric itself, the experiment infrastructure becomes the instrument, and itself is the subject of study. So the role of the Alveos is for scaling in this case. So originally in this experiment, we were sampling traffic, and this is coming in over 100 gigabit link. But we found that the performance basically was bottlenecked to about 8.5 gigabits per second. And the setup we're using initially was essentially running TCP dump, gathering these frames, capturing these PCAP files, and then as a separate offline task, doing the analysis. What we used the Alveus for is essentially we offloaded a bunch of logic to that enabled us to run at line rate. So we offloaded the sampling, the filtering, the truncation, right? Because we don't care about payloads, right? So we truncate the payloads and also the blinding, right? So when it comes to IP addresses, right? So Casey mentioned CryptoPan earlier. We don't implement CryptoPan currently. We have a simpler scheme, but that's on the roadmap, right? I'm working with another student that's working on a CryptoPan-related project that's kind of warming up internal knowledge related to that, so that eventually we can move this to the card. So essentially then, and then on the host side, we're also using DPDK because we don't want to have to go through the kernel network stack, right? So the setup has really helped us get closer to the fire hose. Another application we're looking at is remote attestation when applied to networking. So as you remember from Casey's talk, right? So a lot of the networking infrastructure that we use today and a lot of the protocols we use today weren't designed with security as a first order concern. That kind of came later. And it came also as a result of, scale and usage, unintended kind of ways of manipulating traffic. So there is this idea, remote attestation, about getting evidence about remote equipment, remote resources that you are a stakeholder in, but you do not directly control. The typical example here is, say you're using a CPU on a cloud, on a commercial cloud. You want it to run software, and you want to get some evidence that it is indeed running the software that you asked it to run. And then it also gets a bit more fancy, right? So not only do you get integrity guarantees, but you can also get confidentiality guarantees. In this case, we're only looking at integrity. So what this project is about is you are a stakeholder in a network. If you are sending and receiving traffic over that network, what do you know and what guarantees can you be given about, in a meaningful way, the configuration of the various parts of that network? And it gets obviously more complicated if there are multiple networks. So the way we're approaching this is in a couple of ways, but essentially augmenting the fundamental objective of modern day networking, which is reachability, with metadata that talks about the kind of an image of the configuration of the devices that it encounters, that your traffic encounters along the way. So essentially, these devices, they bleed a little bit of that configuration, and that sort of taint allows you as a peer that is a kind of a stakeholder that is communicating on this network to, at a different time scale, make inferences about what this configuration is. And then kind of reconcile that with what you thought that the configuration was, or what you were promised that the configuration would be. So the goal here is, as I mentioned earlier, cybersecurity oriented, right? So essentially here, the goal is early detection of misconfigurations to avoid outages in the case of unwitting misconfigurations, and in case of witting misconfigurations, to detect APTs, right? So advanced persistent threat, where you might have a campaign that is subtly running in the background for a long period of time, right? And that would hinge upon exploiting misconfiguration. So there are various ways of approaching this, and indeed we're exploring several. So one approach, which was demoed by Alexander on Tuesday, involves getting a third-party software switch, augmenting it to essentially sandbox the part that you can reconfigure. In this case, it's a programmable switch. So you in case you have had a bait and switch and the P4 program has been changed, or in case the P4 program is exploiting some behavior that leads to different behavior, and there are studies about this that we leverage. So the sandbox essentially allows you to get an image that is essentially a hash of what the P4 program is doing. And same for the state, right? So, and then it deposits that in frames and sends it along for verification. Another approach we're exploring, which Hyunsuk developed, is let's say we don't have the authority to change those switches, right? So we're going to work with black box switches, right? Third-party switches. What can we build around those switches in order to secure them? Right. So the idea here is, and this is where the alveos come in, is to sandwich third-party equipment in order to provide kind of an external root of trust that is arguably weaker than being able to sandbox them, but maybe more pragmatic, right? Because you can't change equipment that you bought that's in place, but maybe you can build stuff around it to improve its transparency and its integrity. And should you wish to find out more about this, happy to talk more offline. Okay, so those are examples where alveos played critical roles in enabling us to explore interesting use cases and scale. So now I'm going to turn to the next phase, which is about how do we actually use them, right? So now I'm getting to the starter kit I promised you at the start. So essentially, we're going to organize work into two phases. There's going to be the development phase that's going to take place outside of Fabric for reasons to do with practicality, right? So doing the compilation job on these things takes hours, and you don't want to take up testbed time that other people could be using on this, right? So we do this on our own servers or laptops. You get an image from that then you use for an experiment inside Fabric, right? So I'll be telling you a bit about both. So for the development phase, obviously, we'll be needing to use, languages and tool chains. And for the experiment phase, I'll tell you about how we go about doing the allocation and about doing the configuration of these resources on Fabric once we have done an allocation. So here's the plan. We're going to be looking at the development process, in this case, specifically using the SNet SmartNIC framework, allocating the necessary resources on Fabric, deploying a program on the Alveo that has been developed in step 1. We're going to be running and testing a program. And because typically it's good to be able to know more in case we need to do any debugging, how to do diagnosis, right? What does that look like on this platform? And I won't cover recompilation simply because the time scale is kind of incongruous with the time we have today. So here I'm going to tell you a bit more about the SmartNIC platform, right, and what it really gives you, because it essentially provides a context, an architecture that allows you to slot in the specific logic that you want to change, to introduce into kind of that middle box over there. Middle box is two separate words, not in the networking sense. And not have to deal with this super important but super difficult to get right task of pipelining and integrating the various other logic blocks, right, that you can see here in order to have line rates, performance happening across multiple links. So what we're going to be doing really in this case is focusing on writing P4 programs that are going to get compiled and integrated with this overall design. And this is then we're going to be using the vendor's compiler to produce a bit stream that integrates or that includes all of this design that will then ultimately configure the FPGA. And I'll tell you a bit more about parts of this geography later on. But that's the big picture, right? And that's the kind of the extensibility angle that I mentioned earlier, right? That's, it's easy to get started and you can pay for what you use and use, and carry out customizations should you so wish. So this brings us to the programming part and to the P4 part, right? So what we're going to be looking at is how do we specify and how do we parse headers? In the example I gave you earlier, we used a custom header, right? We didn't even use IP, right? So it was Ethernet and then this header immediately after that. We're going to look at how to specify program logic, and the basic bread and butter in this paradigm is tables and lookups. So over those tables and subsequent actions. So I'll be showing you a little bit about how that works for the example we looked at. So starting with headers, the syntax is very familiar. If you've done something like C, essentially it is a serializable form of a struct, right, without any unexpected kind of struct packing that's happening on the compiler for your behalf. And the structure is exactly as you'd expect it to be, right? So you express bit vectors, and you name them, you give them a size, and that gives you something that is going to be populated by the parser, and then ultimately something that you can interrogate or mutate at runtime. And then what happens is, you can see in the gray blocks below, is kind of you gather together the headers that you expect to coexist inside a frame and describe your header stack and instantiate the types that we saw earlier. And now turning to the specification of program logic, what we see here is we have two new panels showing up on the right. Kind of a fairly intuitive syntax of describing consts, right, or hash defines, if you prefer going the untyped route, where we see some of the features that we encountered earlier, right? So if you look at, for example, P4 Calc Plus, you'll see the code for the symbol for addition, for example, right? So essentially that's part of the code that we executed earlier that shows up in syntax form. And we have similar consts for the other operators. And in this case of this custom protocol, we also have some other constants, right? So just as in IPv4, you start with the constant 4, right, for your version. In this case, you start with P, and then you follow up with 4. And then what you're looking at in the bottom right quadrant, that's showing you the actual program logic, right? That's followed when a frame arrives. What we do is we first check if we were able to parse the custom header. And if we were not able to parse the custom header, then we call operation drop, right? So we don't even forward it along, we're just going to be dropping it. So for those of you who remember when I showed you the frame count earlier, you saw many frames, it was a few thousand frames came in and only a handful left. That's because there was a lot of background chatter to do with neighbor discovery that essentially were dropped. And the handful of frames that were egressed were the result of calculations that were carried out during testing. So if the P4 calc header is valid, then we're going to drop into the second nesting of another if condition, right? So we're going to check that the different fields that we expect to have constant values do indeed have those constant values, right? So the P and the 4 and the version in this case. And if that is satisfied, we apply the table called lookup. Sorry, the table called calculate, and we carry out the lookup. And in a language like P4, tables have a very central role. So in this case, we have the definition of the table referenced earlier, and we are going to be looking up on the op field. So that's the operation, right? So in this case, it's going to be looking to see what value that has, and it's going to match it exactly, and then it's going to take some kind of action. And it provides us, we have here a list of actions such as operation add, subtract, and so forth. And by default, it's going to be dropping it. So what's going to happen if, for example, it is a valid it has a header that conforms to the specification, but it has it's describing an operation, or it's asking to use an operation that does not result in a successful lookup, right? It does not result in a hit. In that case, you're still going to be dropping the frame. So what does an action look like, right? So now kind of progressing to the next level. Starting with action add over there. So what we have, the key thing to look for is that P4 level addition, right? So, the ASCII code that we saw earlier, that was just a symbol, and that addition symbol there is another symbol, but it's at the P4 level, right? So essentially we are taking, we are internalizing the operation to carry out, to interpret it with the P4 level. And it behaves exactly as you'd expect, right? So we are adding operand A to operand B, and then we're calling another action called send back. And what sandback does is kind of the logistic steps that follow, which involve getting the result that was computed and pushing that into the right field, the res field, and swapping the source and destination addresses, right? So you might remember this from the diff I showed you at the start. And then finally, it's going to set the egress port to be the same as the ingress port, so that you're kind of bouncing the frame to the same link on which it came in. So that's the P4 logic in a nutshell, right? And as you can see, the syntax is pretty intuitive. Obviously, every language has its own idiosyncrasies, but with some knowledge of C++, it's not that hard to internalize its behavior. Okay, so then how do we go from there to running it on Fabric, and I'm specifically configuring the Alfeos that are on Fabric, right? So for one thing, you need a specific permission that the Fabric project would give you in order to allocate these resources. But the cool thing here is that you would allocate a slice as normal, right? So there's a specific component that you can request using that permission in order to use these smart NICs. But as we'll see, for those of you who have used Fabric, it's going to be very familiar. And then the third phase we're going to reach is configuration, right? So there's kind of a bit of a bring up we need to follow. A lot of it is very templatey and intuitive, right? There's nothing really unexpected here, but essentially we need to configure the hosts, and we need to configure the Alveo card, right, and drop the program there. And finally, we need to configure the program's tables, so for the logic that we just looked at previously to work. Now, the cool thing here is that the program's tables you can update at runtime without having to recompile the program, right? So as we'll see, kind of we can make addition behave differently simply by from the control plane changing the contents of the calculate table. So how do we create a slice? Well, essentially what we need to do for the example we just looked at is have two nodes, have a link between them, and have the tester host have any kind of basic NIC will do. And for the Alveo host, we need to specify that it's going to be a particular type of component. And the name for that in Fabric is FPGA Xilinx U280. And then what happens next is we need to configure this all up as I mentioned earlier, right? And one particular feature here is including container images that the ESNet framework relies upon. So some of these images we will build externally and import. One of those images we'll have to build on the platform. But there's a learning curve to everything, right? And initially it might seem very kind of unfamiliar and bureaucratic, but I'll give you a kind of a recipe to follow at the very end that can kind of streamline all of this for you. So in order to configure this Alveo card, the workflow we follow is we get the bitstream, the artifact that we created during the development phase, and essentially move it to create an image that we're using to configure the card during the experiment phase. So the kind of the stack you can see on the right, that's taking place inside Fabric, and the kind of the blue part, that's the blue square that's taking place on your development machine. So you start with the P4 program, generate the bitstream, and that provides one input. The other input is the configuration, which you can dynamically update on Fabric directly. So what we'll see is we'll see some tools that allow us to do some of this configuration. So there is in a bit. But before we get there, I want to show you another tool which is P4 specific, right? So once we've done the configuration, we're going to need to add and remove, add those entries in the table in order to be able to have addition behave as addition, right, and subtraction behave as subtraction. But something I'll show you is, and this obviously is trivial for the calculator example we're looking at, but something I'll show you is the ability to kind of swap rules around and update them, which becomes more interesting in more more sophisticated examples. So here, what I'm showing you is running in the tester node. Instead of going to the Jupyter Notebook interface, I'm running a script that's doing this calculation. And I'm requesting different types of operations, right? Addition, subtraction, we have XOR, we have and logical OR. So now on the Alveo side, what I'm going to do is I'm going to enter the container so that I can issue commands directly to the card from the environment with all the dependencies built in. And so I'm using this SNPF4 CLI tool, and you can see it's various options. And the option I'm going to go for is clear all. So this is going to delete all the entries in the tables. So now I'm going to try rerunning some of these operations. And essentially, the packet is being dropped, right? So the script I'm running, it has a little timeout, and after a while, it'll give up and say, I didn't receive a response. So whatever operation you're going to try to run, you're always going to get the same reply, because that table, that calculate table that we saw that drives the logic for this program is missing every single lookup, and so the default operation then is to drop. Okay, so now let's proceed to the next phase. So in the next phase, I'm going to run the same tool, but I'm now going to repopulate some of those rules. And essentially, I'm going to say, I want to populate the calculate table, and I want the action to be operation add, and I'm going to match against 2b, which is the addition symbol in ASCII. Good, that works. Now I'm going to try using a different operation. And yeah, that doesn't work because we only have one rule now over there. So that's the only thing we're working for. And now I'm going to try adding 5e, which is the carré symbol. Okay. So in this case, addition and XOR, they give the same result. So now what I'm going to do is I'm going to clear everything again. And I verify that by trying to rerun the calculation, and I'm not getting a response. And now the final step. For the final step, what I'm going to do is I'm going to say, OK, I'm going to use the plus symbol, but I'm going to map that to subtraction. And that's 2D, so that is the minus symbol, and I'm going to map that to addition. So if I have 3 minus 1, it behaves as an addition, and if I have 3 plus 1, it actually behaves as subtraction. And as you can see, that is instantaneous, right? So doing the compilation job for a program, that takes a couple of hours. But there's this runtime reconfigurability feature that comes in very handy. OK, so I promised you kind of earlier kind of looking at the big picture in terms of configuration and the containers. So the way I've gone about this is I created a notebook, and it kind of stitches together all these phases, so that essentially running the notebook will have you ending up with a working system. And we're going to be looking at this notebook. So what you're seeing at the top is kind of the boilerplate of kind of initializing some very basic objects we're going to be looking at. And then in this field after that, I'm setting some constants to do with where we're going to instantiate this, and where we're going to be obtaining some of these images from. These images we don't share, so you need to have an account with AMD in order to have the components in order to build them. But for universities, that's very straightforward. And the topology that we're going to build is is kind of the picture we looked at earlier. I've put in some more details here since the NICs actually have 2 ports, right? So we name them separately, even though we're only been using one single link. And what we do to create the slice, you can see it in the top cell over there. It's pretty intuitive, right? If you used Fabric before, you've probably done this a lot. The key delta to look at is in the 3rd line of syntax where we have FPGA Xilinx U280, right? So that is where we are kind of specifying that we're going to be using this component, and we are going to be attaching this component to node 1, which is the kind of syntax name for what we devised earlier, which is the Alveo host. So you work through all that, right? So this essentially kind of puts in syntax form what I showed you earlier in a block diagram, then called slice submit, and the Fabric backend will make these resources available to you. So then what happens after that is we configure hosts. So there we go. This basically involves downloading dependencies that parts of the system are going to use, and moving. As you can see, I'm uploading some scripts there in order to make them available for runtime. So I'm uploading in the second cell, I'm uploading the calculation script, for example, that is used by the notebook in order to ferry these requests along the way. And then things get a bit more kind of specific, right? So we install a bunch of dependencies for ESNet's SmartNICs framework, right? So I mentioned it's very kind of container oriented, right? So we install some dependencies related to that. And download some containers. So a lot of this is kind of cookie cutter. And then we get to building the container, right? So now we've in this step we've reached the stage where we can start configuring the NIC. And in the cell, what happens is once you've built the container, you can bring it back, you can bring it up, and starts to get indications of success. And the first indication of success you can get, at least the one I ask for habitually, is getting the version information from the runtime. And this was the version information, incidentally, that I showed you in the notebook earlier, right? That query script ferried. But in this case, it's kind of a more primitive way of doing that. So then what happens after that is you configure the card itself, and remember what I showed you earlier, right? The kind of the block diagram, the top level design of the card. You have a little network that's running there, and one of the cool things about the design is that you can configure the topology of that network, right? So you can bypass certain elements, for example, or you can just have something behaving as a loop back, right? So you want to cut out certain logic just to make sure that you can make it past, past the MAC layer, MAC block, for example, and then come back over the link. So at the end, I'll share some documentation that goes into this more detail. For the purposes of this talk, I won't go very deep, but basically this next block configures the topology of that network in the design. And then we come to configuring the program. And this is where we use the rules that I showed you in the demonstration earlier, right? So for every single operation, we have an entry. And what that entry does is it says, if you see this symbol, then run this operation, right? And as you saw earlier, kind of you can switch symbols around, right? Or if you update the program, you can also add additional actions that it can interpret and map it to additional symbols. But in all of this, as you notice, kind of you don't have like a main function, right? So essentially, once that container is up, the program is already running. And then finally, this last in the middle of the screen here, you can see an invocation, a manual invocation of a calculation of the kind I showed you from the console earlier. And the last bit of this notebook involves simply shutting things down and returning the resources back to Fabric. Okay, this has been quite a fast tour. So I've checked some things off our list there. We've seen the first three things. What I want to tell you next is about how to run and test programs and doing diagnosis. So the running part, there is nothing you need to do, actually. So once the thing is up, it's already running, right? It's already going to be responsive to frames that are going to be coming in over its interfaces. So I'm going to be focusing on the testing part. And here, testing part, I'm going to stay with the running example that we have, right? I'm going to stay with calculation. And here, testing involves crafting those packets that we are using to make those calculation requests, and then interpreting those replies that's returned. For this, we're using Scapy. And essentially, so here you're seeing P4. Actually, you should be seeing Python. But what happens is that in Scapy, we encode the exact same structure that we encoded earlier in P4, right? Because they need to interoperate. And what the Python code will do is essentially stack that P4 calc header over Ethernet, right, and specify some fields, specifically the operation and the operands that it parses from that command line argument that I gave earlier, and then craft a packet that's sent over a specific interface. Makes it over the link, hits the alveo, comes back. The script will then parse the frame that comes back and print the results to the console. So this brings us to diagnosis. So in the top level design I showed you earlier, you might have noticed this section here. It has some counters. And you can see these counters, they are peppered across the design, right? So we find these to be very useful because we essentially follow the values of these counters as traffic makes it through the design. And we can notice whether a frame was inadvertently or unexpectedly rather dropped by the P4 block if, for example, the counters that follow the P4 program are not incrementing as we would expect, or as not at the rate that the preceding counters are. So we've used this to do a variety of different, this has helped us out in a variety of different use cases. For diagnosis, I should also mention that you don't have to test this on hardware every single time, right? So there are gentler approaches. And in the documentation I'll share, it explains how you can run different types of simulations so that you can get quick feedback to test whether the logic is actually working the way you intended. And what you're testing at the hardware level is also kind of the integration of your P4 logic with the top level design that's running on the device. Okay, so now what I'm showing you is actually polling those counters, right? So as before, I'm going to enter the same container and invoke a command that'll get the probe stats. All right. So what you can see here are we're looking at. So we're looking at packets or frames rather that made it in some number through both of those ports that you saw in the picture at the beginning. So in this case, at the time I took this, we can see that there were about 7,300 frames that showed up on both of those ports, and this is referring to a counter that's after the MAC block. And what we can see is from the previous highlights that all of those were forwarded to the P4 program, right? So essentially, add the two numbers, you get the roughly 14K value. But then looking at the egress from the P4 application, you see quite a disparity, right? So only nine packets came out. And the reasoning here is what I mentioned earlier, right? That a lot of those packets, a lot of those 7,000 packets on each port were management packets, right? They weren't packets that the logic in the P4 program was prepared to handle. So its default behavior was just to drop them. So then what we see here is the P4 program returns 4 packets to the rest of the architecture, and these 9 packets then make it to CMAX 0, which is on the other side of which is the link to the tester host. Okay, so what I've shown you so far is kind of like an end-to-end kind of composition, right? Starting with a program, seeing it work, and then looking at how the program is defined, how to put it on Fabric, right? How to use this infrastructure, and how to do some runtime polling and manipulation of the state of these Alveo cards. So to end with, I'm gonna end with pointers on what I promised you at the start, which is the actionable path, right? So that you can start using them. Before I get to that, however, super important, I want to thank the people that I've been working with. So basically the students and staff at IIT, who you can see in the top block there, and the people who are underlined have not only used Fabric, but also used the Alveos on Fabric. And in addition to that, a huge thanks to the people in the community across various organizations who made this possible and provided different types of support, right? So including Fabric, but also a variety of different organizations. And that this has been very enriching both for me and also for the group I work with, allowing us to reach new technical capabilities that we're applying for our research. Okay, so how to get started then? Well, one thing is I want to point out the Fabric forum. So there's one specific forum that is scoped to using this resource. So that's the go-to place for this. But ultimately, the thing I wanted to share was a starter kit that encapsulates everything I've covered in this talk, including the notebooks and the scripts, right? So and also including a write-up of what I've just described, right? So that you can read that and you can get those materials, and hopefully that can help bootstrap your own use of these resources on Fabric. Okay, thank you.
Yes, this was very great. Are there any questions from the audience? Case always has a question.
Well, actually, I don't have a question, but I want to do some shameless self-promotion. So I would like to remark that we will have at Supercomputing another instantiation of the Indis workshop. That's a full-day workshop on Sunday. It gives also from this testbed and from NRP and so on, the students and faculty the opportunity to publish papers and to get talks and keynotes for your normal scientific CV. So watch the space. The workshop was just earlier this week approved, but it is a great opportunity to also publish to the supercomputing and internet community your work, what you do on Fabric. Thank you.
Yeah, we're really going to promote a lot of our Fabric users to try to submit to Indis because it's a great place. I think the last Indis, a lot of the papers were actually Fabric related, so it was really good. And Andrew's got a question.
So Nick, thank you for so clearly walking us through. I have a question. What is next? Like, how can this capability, or you with the students in this capability, work with scientists or users that would benefit from doing this in network computation using the FPGAs? How do we take it to the next step?
Thanks. Yeah, great question. So I see kind of two interrelated activities. One is kind of part of what I've been doing, which is capacity building and more on the education side, putting students into contact with resources and infrastructure and the dynamics that they typically wouldn't encounter in a university course, in order to actualize some of the challenges that people encounter in operations, right? And feeding that into research, which then can use that experience and that knowledge, but also that energy, that enthusiasm to solve novel problems. For my case, what I'm looking at primarily are those two areas, right? Cybersecurity and continuing to refine prototypes that allow people, stakeholders of a network, to verify its integrity up to some limit, obviously, but to have some kind of negotiated arrangement whereby they could get more transparency into the resources they use. And the other direction is in science, right? So networks related for research, both Fabric, but also with particularly with Fermilab, looking at their use cases that have very specific characteristics, and thinking about how can programmable networking can make their life easier, right? In terms of easier maintenance or maybe cost saving, right? As well as being able to scale up to meet the increasing demands of their instruments.
Thank you.
Thank you.
Any other questions? So let's think again.